want to just go? Great.
Hey, welcome everyone. It's great to see so many people here in person, even with the questionable weather outside today. It's my pleasure today to introduce the CISL seminar speaker, Moha Gharamti. Moha earned his bachelor's degree in geological engineering from the Middle East Technical University in Ankara, Turkey, and later got his PhD in earth sciences and engineering from King Abdullah University of Science and Technology in Saudi Arabia. After his PhD, he had an 18-month postdoc in Norway, so moving from Saudi Arabia to Norway has prepared you for all climates. At the Nansen Environmental and Remote Sensing Center, also known as NERSC. There's multiple NERSCs in Norway, so it's very confusing, in Bergen. He's been here at NCAR in the Data Assimilation Research Section in CISL for 8 years now, doing all kinds of cool theoretical and applied data assimilation work. And today he's going to talk about stuff he's been doing on all kinds of aspects of novel flood prediction systems. Go away, Moha. Oh. And if you could hold questions till the end on this, and online questions will be via Slido, which we'll monitor at the end. Okay,
thanks. Thank you, Jeff, and thanks for everyone who is tuning in today to listen to this seminar talk, whether in person or online, after a very long and chilly weekend. Today, I plan to take you with me on a journey over the last 6 or 7 years where we developed a flood prediction system using advanced data assimilation techniques. Before I start, I would like to thank my excellent collaborators. In particular, I would like to thank Arizu from the HAB team in RAL. Arizu has been instrumental working closely with me throughout this work. Also, I would like to thank James and Tim, who helped us tremendously during the initial phase of the work. And of course, not to forget the entire team from the data assimilation research section. This is the outline of my talk. I'll start by motivating the flood prediction problem, and then I'll introduce our flood prediction system, HydroDART, with its 3 different components: the model, the data, and the data assimilation framework. And then in section 3, I'm going to talk to you about the kind of advanced data assimilation tools and algorithms that we developed as part of this work. And by the end of this seminar, I'll talk to you about our current activities and what we plan to do in the future. So to start with, I'm showing you here a cartoon of stream flow conditions across the US. So essentially, in each tile, you're looking at percent of stream gauges by flow levels using percentiles relative to historic record at each site. This essentially would tell us whether stream flow have been, higher or smaller than what was experienced at each site in the past. And now, if you focus on the Florida tile, you'll see that wetter than normal conditions have been observed, and this is coming from September of last year. Florida was hit with Hurricane Helene by the end of September last year, causing massive flooding across the state. In the rest of the country, we see drier conditions. Now, by the time October came in, unfortunately for the people of the Sunshine State, they couldn't catch a break because Hurricane Milton made landfall, causing massive flooding, not only in Florida, but also in other coastal cities such as Georgia and Carolinas. So we're talking about these extreme rainfall events and hurricanes, and the associated flooding that comes with them. These have been consistent recurring events, throughout the years. In fact, these are considered billion-dollar disasters, and they go all the way back to the 1980s. So if you count all the damages since that time, we're talking about almost $1 trillion in damages because of these, extreme events. These hurricanes are usually described as subtropical or tropical cyclogenesis that they form in the Atlantic Ocean. We measure them usually based on the Saffir-Simpson scale for hurricane wind speeds. Last year, Hurricane Helene was the most destructive one with wind speeds up to 140 miles per hour. On top of their destructive wind speeds and storm surges, these hurricanes can unleash almost 2.5 trillion gallons of water a day, causing what we call freshwater or inland flooding. So this is where the water flood on the banks of the streams into the coastal communities, causing catastrophic damages to infrastructures and to lives. So we asked ourselves, how well we can predict these flooding events, and what we can do to improve on the current capabilities that we have in our current systems. So we started developing our hydrologic prediction system, HydroDart. So this is a system that integrates weather research and forecasting hydrological model WRF-Hydro together with the data assimilation research testbed DART. With HydroDart, you're able to get hourly and sub-hourly stream flow assimilation. It is a highly robust prediction framework using state-of-the-art data assimilation tools. The model code and the data assimilation code are coupled, and we use a Python wrapper to integrate these two softwares. For configuring experiments, we use YAML files, and we provide advanced diagnostic packages in both MATLAB and R. For people who are interested to look more at our prediction system, to look at the code and read more about it, they can refer to our repo on GitHub. So there are three different components in this system. We'll start with the model. So the model WRF-Hydro is the research component of the National Water Model, or NWM. WRF-Hydro is a community-based system. It's able to simulate major water cycle components, providing reliable stream flow predictions. What you're looking at on the right here is a stream flow simulation from the months of September last year using version 3.0 of the National Water Model. The model code is open source. At the bottom, I'm providing some useful links for those who are interested in looking at the model and reading more about it. Now, as far as the modeling structure, so starting from the atmospheric driver, which feeds into the land surface model, or the LSM, which is NOMP in this case. NOMP is coupled to a terrain routing module, which runs actually on a finer scale, 250 meters scale compared to a 1 kilometer land model. As far as this seminar talk goes today, we are going to be focusing on a catchment scale, essentially looking at the channel and the subsurface routing modules. We will look closely at what's happening in the stream and in the subsurface groundwater. For the data, we use stream flow data. These data are available, going all the way back to 1889. Back then, they were manually collected, as you see in the picture, by the hydrographer at a site in New Mexico. Thankfully, since then, the process has been automated, and the USGS, or the United States Geological Survey, now operates a network of almost 10,000 gauges nationwide. Now, these stream gauges, I'm pretty sure you've seen one of them. These are metal structures usually placed on the side of the highway. They're able to collect water data and transmit them in real time. You can get information about water levels, flow rates, and many other quality data that we will get to by the end of this seminar. As far as the data assimilation framework, like we said, we will use the Data Assimilation Research Testbed, or DART, which is a community facility for Ensemble DA that is developed and maintained by the DERIS section in CISL. You can conduct many activities with DART. Essentially, you can do ensemble forecasting, reanalysis, to model improvement through parameter estimation. You can do sensitivity analysis, observing system simulation experiments, and you can test your favorite data assimilation algorithms. What I'm showing here on the right is a figure with all the geophysical models that are supported in DART. Obviously, today we are going to focus on WRF-Hydro. And on the top, again, some useful links if you're interested in looking more at the code and documentation. Okay, so these are the three different components of the system. In order to test the performance of the flood prediction system, we are going to look at three flooding scenarios in here. So on the far left, you're looking at flooding caused by Hurricane Florence in North Carolina in 2018. So this was a Category 4 hurricane that made landfall around mid-September. With damages up to $25 billion. The second case is a flash flood, or more of a short-lived flooding event in West Virginia that was caused due to several thunderstorms in June 2016. This event was so extreme that the area experienced around 8 to 10 inches of rainfall within a 12-hour period. And then for the third case, we are going to look at Hurricane Ian in Florida. So this happened in September of 2022. This was the 5th strongest on US record with damages up to $112 billion. And unfortunately, around 150 people lost their lives. So coming to our data assimilation approach and the kind of algorithms and tools we utilize to solve this problem, I'm starting here by Bayes' theorem, and the goal is to essentially compute or find the probability density function of a state x, which can be stream flow in here, conditioned on available observations, which can be gauge flow data. Now, using Bayes, this is nothing but the product of a prior distribution of my state and a likelihood observation function. So in 1D, how does that look like? So imagine we have a prior distribution in green that you can see in here. So I'm looking at the stream flow here on the x-axis and the density on the y-axis. And then I get an observation from the gauge data that is centered at around 0.8, that has a mode at around 0.8. Now, combining these two things together, I get this kind of posterior that still have these two modes. However, the leading mode of the distribution is centered closer to the observation. Now, solving this in a higher dimension, integrating this whole, the PDFs using Bayes in higher dimension is pretty difficult. So we will be using the sequential ensemble common filter to approach that. Now, the ensemble common filter, or the ENCAF, essentially approximates these distributions using an ensemble or a set of model realizations. So every time, as you can see here on the far left, the model is being integrated not only once, but several times, depending on the size of my ensemble. The other thing here, you can see that these distributions are nicely looking circular and elliptic in shape, so we assume them to be Gaussian. And one other characteristic about the ENCAF is that it's a recursive algorithm. So whatever I have posterior, for instance, if you look at time tk, the posterior in red becomes the prior at time tk plus 1 whenever a new observation comes in. So overall, for each data assimilation cycle, the ENCAF will operate into successive propagation or forecast steps, where the model is being integrated, and an update or analysis step where the observations get used. So these are like the major, I would say, equations of the ENCAF. So I'm looking at the prior distribution on the top. Again, this is Gaussian with the first two moments. The first one is the ensemble mean. So that's nothing but the average of the model realizations. And then the second one is the sample background covariance matrix. As far as the distribution at the bottom, so this is the posterior, and it is centered at XA. So XA is the analysis ensemble mean or posterior ensemble mean. And the solution you see there is nothing but the blue, or the best linear unbiased estimator. And I guess what I would like you to focus on here is this background covariance matrix. So it appears in different parts of the equations of the ENCAF. So essentially, having an accurate estimate of this background covariance matrix is really essential for the ENCAF to perform properly and to have for you to have a healthy data assimilation system. And in fact, one of the major players, contributing to the accuracy of this background covariance matrix is N in here, which is nothing but the ensemble size. And just to illustrate you how the importance of this ensemble size, imagine we have a bimodal distribution that you see here on your screen. And I know exactly how to draw samples from this distribution. And the question is how many samples I need before I have a good representation of this PDF. Would 40 members be enough? Well, obviously not so much, because I almost completely missed the other half of the distribution. What happens when I increase that to 80 members? So it's getting better. And then if I increase that all the way to 400, things get better and better. So it becomes clear that having or we would definitely need a very large ensemble size to approximate these complex distributions. But not so fast, because there is no free lunch, and with geophysical models, we can't really afford running large ensemble sizes. So if we're stuck with a limited ensemble size, then we will have to deal with what we call sampling errors. And just to illustrate what sampling errors refer to here, if you focus on the figure to the right, I'm trying to correlate here two independent random variables. Now, ideally, the correlation should be 0 because they are independent. But if I represent them by a limited size ensemble, you'll see that with 8 members, for instance, the correlation error between these two variables is non-zero. It only goes all the way to 0 for very large ensemble sizes. And we know that from Monte Carlo sampling that the rate of convergence is inversely proportional to the square root of n, and n here is the ensemble size. So with sampling errors, what I might expect the true variance to be underestimated. And then with these sample covariance matrices, they can be rank deficient because I'm trying to represent a very large number of model variables using a very small sized ensemble. And then I guess the more challenging issue, if you look at the figure at the bottom, comparing the true covariance to a sample covariance, you see that the sample covariance is really noisy. So everything you see of the diagonal elements is what we call spurious correlations. Or in other words, you can think about them that these are fake, like incorrect correlations. They shouldn't exist. They are just there because I am representing this whole thing with a small n, with a small ensemble. On top of sampling errors, I'm working with error system models, so I am, model errors or model biases are unavoidable. And in the case of stream flow prediction here, this could be coming from uncertain parameters. It could be issues in the forcings. And then, there's also the question of physical variability. If the model doesn't have, enough error growth in it, so talking about stream flow conditions, when I have low flow conditions, I wouldn't have enough spread in my ensemble to be able to represent the true variability in the system. Now, all of these things would combine together, in your data assimilation experiments and degrade the estimate of the sample background covariance. So what we'd be left with is a noisy, inaccurate, and underestimated covariance that would definitely lead to suboptimal updates. So I guess the research question is is, starting from this PF, what can I do to, how can I aid this sample covariance matrix to make it look as close as possible to the true covariance, which is unknown, by the way. We will attempt to answer this. We will look at these 3 different problems in our system, and we'll try to address them separately. So starting with the physical variability, we asked ourselves, working with WRF-Hydro, how can I generate this model-induced variability, especially that would be really helpful for me, especially in low flow conditions. So we developed what we call a multi-configuration ensemble. So if you look at this cartoon as if it's like a cross-section of your compound channel where the water is running, so it's characterized by different parameters, different width and different roughness. And we know for a fact that these parameters are uncertain. What we did is we actually perturbed these channel parameters, and we ended up with an ensemble that is, for every member, it's running different configuration of the channel. And the next thing we did is that we generated ensemble perturbations to the boundary and the surface fluxes, both that are going to the subsurface and the surface model. So just by doing this, by following this multi-configuration approach, you would end up with having this kind of internal variability that is already generated by the model itself without having to do anything externally. So I guess going back now to the drawing board, so whatever you see here in vertical boxes, so this is kind of an upstream offline model that is feeding the fluxes into our data assimilation system. So we perturb these fluxes, and then on top of all of that, we also perturb the channel parameters. And just to denote that what we just did, the multi-configuration ensemble, I'm going to add a hat over my sample covariance matrix, and I'm going to build over that. Okay. Now next, we looked at sampling errors, and for sampling errors, we looked at localization. So localization is a method that is widely used in NWP system or numerical weather prediction. It's a way to limit the impact of an observation to nearby state variables. So if you look at the figure on the right, So on the top, we have a correlation, that were obtained from a 25-member ensemble. And right below that is the one obtained from a 200-member ensemble. Obviously, the 200-member one is way less noisy than the 25-member one. Now, with localization, we construct this row that you see on the right-hand side of your screen, or what we call it a tapering correlation function. And we apply what we call a short product or an element-wise multiplication with your sample covariance matrix. Now, if you do that, you will see the result at the bottom. So with the localized ensemble covariance with 25 members, now it's a lot less noisier than what we started with. And it looks like it really came from a 200-member ensemble. Now, in covariance form, this is going to be the same thing, but in covariance form, looking at the top right figure here, assuming this is the true covariance, and the noisy one on the right, this is the ensemble covariance. Like we said, we construct this tapering correlation function. And then when we do a sure product, we end up with the localized ensemble covariance at the bottom. Now you'll see we got rid of that noise. And it's starting to look a lot like the true covariance. But can I do the same thing here for streamflow, for the streamflow system that I have? Now, note that I'm working now with a stream network, which is really an unstructured grid. So how am I going to really localize the impact of gauges to nearby streams? So for that, we developed along the stream localization. ATS localization, this is a new way to localize across the stream network. It's a topological-based technique where you adhere to the stream network, thereby improving the propagation of information. And the whole idea here is that you want to only consider the reaches that are upstream and downstream from your gauge to be impacted by the observation. The other thing is that if you have observations in different gauges, in different basins, or in different watersheds, they shouldn't have any common reaches in between, just because they live in they are not physically connected to each other. So in a sense, if you look at that, we're not only solving for spurious correlations, but we're actually getting rid of physically incorrect correlations between unconnected state variables. And that's what you see here in the subplot where I denoted by Y. Following this, you would get these tree-like shapes, as you can see in the X subfigure, where downstream from the gauge, information will only flow downstream. So to test the performance of this new localization strategy, we're going to look at hydrographs at Tar River here in North Carolina. So we're looking at the Florence flooding in this case. The figure on the left, this is a result from ATS localization, and the figure on the right is the result from regular localization. And I'm gonna change the localization radius in a moment. And that's just to explain what's happening here. A hydrograph is really a hydrologic term for a time series of stream flow. Now on the left, we have the green asterisks are the observed stream flow or the gauge data. Whenever they are shown in red, that means the data assimilation system rejected them just because the observation was far enough from my ensemble mean, so I didn't know what to do with it. The orange or the yellow curve is the open loop, or otherwise known as the free run or the no data assimilation run. Anything in gray and black represent the prior ensemble members and the prior ensemble mean. Anything in blue represent the posterior distribution. And what I would like you to focus here are the RMSE values, the differences between the open loop prior ensemble mean and the posterior mean as compared to what we get from the regular localization. The ATS localization is run with 100 kilometers. So we run some sensitivity experiments and we found out that this gave us the best results. And I'm gonna show you regular localization with different radii. Now with 1 kilometer here, as you can see on the right, the system rejected almost 50% of the observations. I'm unable to fit the rising limb of the hydrograph, and even after a session, I don't have a great fit to the observed stream flow. If I increase that to 2 kilometer, it even gets worse. 5 kilometer, things starting to improve. We see that the rising limb, we have a better fit in here. 10 kilometer, it looks like it's going well, but then with 20 kilometer, it starts getting worse again. And that, if you recall, where I told you about the different catchments, I'm starting to correlate observations with state variables that don't live in the same watersheds. And essentially, this would generate these noisy correlations for me that would degrade the estimates of my system. So overall, across all the gauges, we found that the new localization scheme is able to enhance the prediction accuracy by up to 40%. And with the regular localization, this fails to provide me reliable estimates with very large distances. So what we looked at so far, we worked with a multi-configuration ensemble to generate this internal variability. We looked at sampling errors through ATS localization, and now we are going to look at how to counteract the underestimated variance through inflation. So inflation is really a method or a way to increase the ensemble variance where you can keep the ensemble mean unchanged. It's really equivalent to scaling the covariance matrix. So if you look at this equation in here, assuming that these are what we call anomalies or the departure from the mean, so we scale them by this factor in here, and then we add the mean to keep it the same. This would essentially be equivalent to scaling the whole covariance with this lambda factor. So what does that actually look like? So to illustrate this, imagine we have a prior ensemble of 10 members in here. I can construct a prior PDF that is centered at XF. And then if I have an observation centered at 2, using Bayes, as we just saw, this is the posterior that we get. Now, what if I actually went ahead and I inflated the original sample? So I went from these green asterisks to the green triangles. Now, the distribution is still centered at XF. However, as you can see, it has larger variability. The distribution is fat compared to the previous one. Now, if I go ahead and multiply the green dash distribution with the blue likelihood, this is the new posterior that I get. And obviously, comparing to the previous solid red one, this is closer to the observation and a lot more accurate. But then, this is great. How can I choose the value for lambda? Does it have to be the same across the stream network? Does it evolve in time? What is the best way to choose it? And for that, I actually worked on a spatially and temporally varying adaptive inflation scheme in which the inflation factor lambda is assumed to be a random variable. And I'm going to go ahead and use the stream flow observations to actually update my estimate of lambda, not only in space, but also in time. So if you're interested, this is the work from 2018. In this case, I assign inverse gamma distributions for the inflation factor. And following this scheme, these are the kind of inflation maps you get for stream flow in this case. Again, you will see these tree-like structures because we are applying the same along the stream localization strategy in here. I'm not going to go into details of this, but this is just to show you that there is some interesting and sophisticated math behind this adaptive inflation algorithm. And in fact, while I was developing the scheme, I found a very nice geometrical interpretation behind the adaptive inflation scheme. So quickly, if you actually project your background and observation errors on a horizontal plane, it turns out that the true statistics of your system actually live on a circle with certain properties. And your noisy ensemble statistics live on an ellipse. And the idea behind inflation is that you would like to take this ellipse and make it look as closer as possible to your ideal circle. And just to show you how powerful this adaptive inflation scheme is, again, I'm showing you 2 different hydrographs that's near Clayton in North Carolina. The one on the left uses no inflation, and the one on the right utilizes our adaptive inflation scheme. Now, looking at the left one, you'll see that the scheme is rejecting almost 60% of the observations. In fact, if you look at the prior and the posterior mean, they are even worse than what the open loop is giving me. Now, if you look on the right with the adaptive prior inflation, you'll see I have a much better fit to the observations. I'm able to use more to make a better use of the observations. And all of that thanks to the inflation, which you see in here, plotted according to the right y-axis. You see the inflation is able to respond to any deficiencies in the system, whether that's big biases, whether that's limited ensemble spread, and once it improves the statistics in the ensemble, it goes back to 1, which means no inflation. all of that done in the background, adaptively, without any manual intervention by the user. So comparing these two together, looking at the prior and the mean in both hydrographs, we're looking at an increase of accuracy, almost 80% increase in accuracy. And for me, when I work with the adaptive inflation algorithm, I really look at it as as a bias correction tool. And just to illustrate this, when I was analyzing the results again for the Florence flooding domain, I realized that along PD River here in South Carolina, we were adding a lot of water. The data assimilation scheme is really adding water there. So I looked at different gauges on that river, and I'm showing you one of them here near Norwood in South Carolina. So again, this is the observed flow. Obviously, there's a flood that's happening at around September 17. This is the prediction by the model, which actually fails to predict the major flooding event, probably due to forcing issues. These are the priors that we get from HydroDart. And if you compare these two things together, prediction skill improving by 50%, and these are the posteriors that you get. Almost a perfect fit to the observed stream flow. Again, all of that thanks to what the adaptive inflation scheme has given us. You'll see that the adaptive inflation scheme responds aggressively to the bias in the system, injects variability in your ensemble to be able to fit the observations. And then once a recession happens, the adaptive inflation scheme turns itself off because that is additional ensemble variability is not needed anymore. So everything that we talked about so far, from the multi-configuration ensemble, localization scheme, and the adaptive inflation, we studied them thoroughly, and we reported our results for Hurricane Florence flooding in this 2021 HASS manuscript. We also actually tested the same algorithms for Ian's freshwater flooding and West Virginia flash flood. And we found, that our system, HydroDart, is able to consistently outperform the model's performance. And just to, quickly explain these box plots. So we're looking at the RMSE here, or the prior RMSE. And each box plot, you can think about it as summarizing the RMSEs from all the gauges in your domain. This is for all the gauges, and this is for the reference gauges. The reference ones, just think about them that they go through extra monitoring. People might be interested in looking at them more carefully. The numbers at the bottom is just the average from all the RMSEs in this box plot. So again, in both domains, the system was performing really well and generating additional skill in the model in both Ian and West Virginia flash flood. The next thing that we're going to talk about here is the hybrid ensemble variational scheme. I guess to reiterate, we increased the internal variability in the model through the multi-configuration ensemble. We localized the sample covariance matrix using along the stream localization. We inflated the covariance, and now we are going to linearly combine the sample background covariance with a static background covariance matrix, B. Now, this B is a typical covariance that's used in optimal interpolation OI systems or 3D VAR variation systems. And this is done through a hybrid weighting coefficient alpha, which goes between 0 and 1. So essentially, if you set alpha to 1, you would recover your sample background covariance matrix. And if you set it to 0, you would end up with B. So essentially, we are working with an ENOI system or ensemble optimal interpolation system. Anything in between gets you the hybrid form. So just if you think about it, now we have a flow-dependent ensemble that's coming, being updated over time, and then I'm gonna combine it with a climatology that the variation, the background, the static time invariant background covariance matrix from which is we usually estimate it using the climatology. We believe that this hybridization approach provides you with a better estimate of the true covariance. It really can tackle sampling errors, model biases, and as we will see, computational issues all at the same time. To me, I look at the hybrid scheme as when you add this background static background covariance matrix, it actually helps your flow-dependent ensemble access parts of the PDF that were inaccessible for it previously. It gives your ENCF with new correction directions that weren't accessed before. And I guess the main contribution here is the adaptive scheme that I worked on back in 2020. So essentially, this is the algorithm that allows you to, it gives you updated values for alpha both in space and time. Now, for our system, we actually estimated the climatology, the static background covariance using the 42-year retrospective WRF-Hydro model simulation from 1979 to 2020. So just to show you what this climatology would look like, so I'm looking here at the gauge near Tampa in Florida, and you'll see different flooding events from the past, caused by different hurricanes. For instance, this is caused by Hurricane David in 1979. We have flooding due to Hurricane Elena in 1985. Floyd was a major one in 1999. We have Gabrielle in 2001, and 2 flooding peaks here due to Ivan and Jean in 2004, and more recently Irma in 2017. Now, to test the performance of this new hybrid scheme, again, we're going to look at hydrographs. The first case, we're going to look at a gauge near Keysville in the Florida flooding domain. On top here, we're looking at the ENCF, again, 80 members. And on the bottom, we're looking at the hybrid ENCF OI scheme. But then I'm fixing alpha both in space and time to 0.5 or half. Essentially, 50% of the information is coming from the flow-dependent ensemble, and 50% is coming from the climatology. This is the observed flow. This is the prediction from the model. These are the prior ensemble members and prior ensemble mean. You'll see that we have a much improved fit to the flooding peak in here at around September 30th as compared to the ENCF. And these are the posteriors. And if you check the RMS values, the RMS averages in here, we have massive improvement in prediction skill as compared to what the ENCF is suggesting us, which is still a lot more accurate than what the open loop is suggesting. Now, I guess what's interesting here about the hybrid scheme that it gave us some kind of correction that we haven't experienced before. It's not only fitting the flooding peaks well, but if you look at the low flow conditions in here, so prior to the flood and after recession, we have essentially a perfect fit to the observed stream flow. The ENCF is doing a good job, but here it's essentially exceptional performance. Another gauge from the West Virginia flash flood. So same stuff. So this is near Charleston. The ENCF on the top, and the hybrid ENCF OI with a weight of 0.5 at the bottom. This is the model simulation. The model, is flooding after the observed flood, and as you can see, the magnitude is almost 2,000 CMS or cubic meters per second less than what the observations are giving us. These are the prior ensemble members and the prior mean. A lot more improved fit to the rising limb of the hydrograph using the hybrid scheme as compared to the ENCF, and these are the posteriors. And again, the flooding peak is improved, but if you look at the low flow conditions, we have a perfect match. Thanks to the variability that's coming from the climatology in here. So we were very pleased with the prediction skill that the HydroDart is giving us using this new hybrid scheme. But then we asked ourselves, how about the computational efficiency? Can we do something about it? So everything we looked at so far is the ENCF with 80 members and the hybrid scheme with 80 members. We actually run the hybrid scheme, with different ensemble size in the flow-dependent covariance, going all the way to 10, down to 10. And you will see that, all of these experiments outperform the ENCF. And, even with the 10 or 20 members, you're still able to outperform the ENCF using only a quarter of the computational resources. And next, we looked at the adaptive scheme. So this is, again, another gauge from Northport in Florida. On the top, I'm looking at the ENCF with 80 members. So just similar to the stuff we looked at in Hurricane Florence. And in the bottom, I'm looking at the adaptive hybrid scheme, but with only 20 members. So this is a lot more efficient, almost 4 times more efficient than the scheme on the top in here. Also shown to the right, also shown to the bottom here is the evolution of the hybrid weight according to the right y-axis. And you see, even with 20 members, I'm able, the posteriors are able to fit the flooding peak here a lot better than what the NCAR with 80 members can do. So to summarize everything together, so again, these are box plots from the EN domain of the prior RMSE for the open loop, the NCAR with 80 members, and these 3 are the hybrid scheme, one with 20 members, 80 members, and the adaptive one with 20 members. Now, when we looked at this, all of these are comparable, but if we want to take like a method of choice in here, we chose the 20-member with the adaptive variant just because I don't have to manually tune this alpha weighting coefficient myself. So this scheme is giving us robust performance, high quality stream flow, and obviously extremely computationally efficient. And just to finish up with these results, we asked ourselves, what does that mean to us in a forecast mode? So essentially looking at how long would these analysis updates persist in our system over time. So we did these reforecasts. So we're showing the open loop here. And then, starting from these posteriors, we check the forecast at different lead times. This is for the EN domain, and this is for the West Virginia domain. And note that, even after 18 hours, the forecast starting from the adaptive hybrid scheme is still outperforming what the model has given us. And what does that mean is that, we're able to provide these early warnings, up to 18 hours ahead of flood peaks. We're not talking about 1 hour here. We're not talking about minutes. We're talking about 18 hours ahead of flood peaks. The system is able to outperform the model. This is a flood prediction scenario, so minutes and seconds matter. Sometimes seconds could either mean death or life. So to give early warnings up to 18 hours, we thought this could mark, a great advancements in flood and hydrological prediction. Again, for more information about the application of our hybrid scheme for Hurricane Ian and West Virginia, people can refer to our recent article from last year. And switching gears now, coming into current activities, we've been talking over the last couple of months with the USGS about conducting optimal observation design using their new NGWAS system. The USGS is implementing what they call the next generation water observing system using smart and state-of-the-art technologies. These are gauges that will give you a lot more information than what regular gauge would give you. And the question was where to place these new gauges. And we started working with the Delaware River Basin. We're using HydroDart. We constructed observing system simulation experiments to run different scenarios. We actually broke down our domain area into 10 different basins, and we checked the impact between assimilating upstream and downstream gauges. We would like to push this forward, and for next steps, we'd like to optimize, continue to use HydroDart, but essentially guide the placement while optimizing for accuracy and uncertainty. Also, currently, we're doing conus-wide predictions. So we're using HydroDart to perform stream flow prediction across the entire US. Some of the activities that we're doing is sensitivity runs with respect to the ATS localization radius. We're also tuning the climatology, essentially, testing different ways to construct the climatological ensemble. And then we're hoping to get to non-Gaussian filtering because, stream flow is by design non-negative, so a Gaussian distribution doesn't fit so much in that framework. And of course, hopefully, if resources allow, we really hope that we can do a full stream flow reanalysis of the conus domain. On the right, just you can see some preliminary results of the percentage of the RMSE reduction, given by our HydroDart system as compared to the open loop. Going forward, one of the future research activities that we would like to conduct is coupled DA. So on top of streamflow, we would like to integrate the land model, the NOMP, and conduct weekly and strongly coupled DA. Essentially, we would like to study the impact of assimilating soil moisture and snow depth on streamflow and vice versa. We kicked some of this work, on snow DA. Arzu led most of this work, back in 2023. So this is where we assimilated snow depth data from the New York Mesonet gauges, and we looked at the impact on streamflow and several other variables such as soil ice content. On the bottom here, you can see a time series of snow depths, at different lead times, comparing the open loop and the DA runs. We really would like to develop this further and look at comparing weekly versus strongly coupled data assimilation, looking at different variables such as streamflow and the impact it has on streamflow. Next, in the future, actually, this is very soon. We got some funding from USGS on integrating their a new Python-based hydrologic model, which they call PyWatershed, which is essentially replacing their legacy hydrologic model, PRMS, or the precipitation runoff modeling system. So we're going to build an interface to PyWatershed with Dart, mimicking what we have in HydroDart, and we're going to start working on this very soon. And lastly, we are also exploring how can we best take advantage of AI and ML, and how these can benefit our HydroDart system. So the problem we're considering here is the ungauged basins, and for those who are unfamiliar with the term, so an ungauged basin is really a basin with insufficient hydrological data, whether that's by quantity or by quality. In fact, the International Association of Hydrological Sciences considered PUB, or prediction in ungauged basins, as the decadal problem, from 2003 to 2012. So the idea here is that we would like to train a generative AI model over regions where we have a lot of observations, such as the Delaware River Basin, and then we can use it over regions where the observations are very sparse, and generate what we call the pseudo streamflow observations, which can then later be effectively used for model calibration or perhaps assimilation purposes. And the ultimate goal is to enhance the forecast skill of the model. And with that, I would like to stop. Thank you for listening, and take any questions.
Thanks, Moha. We're switched to the roof microphone. So let's start if there are any questions in the room, and then we can see what's out there online. Go ahead, Chris.
Moha, thank you. That was very thorough, and I think I'm following a fair bit of it. This is not my area.
Great.
I did have a question, though, on your slide where you showed an 18-hour lead time when you actually integrate a forecast, and it's a statistical question.
Yeah.
Those look like box and whisker plots, and while the mean looks a little lower out at 18 hours, yeah, there's a lot of spread.
Correct.
So
Correct.
What is the really useful, the statistically robust time scale? I mean, it looks like there's a slight difference way out there, but I don't know if it's statistically significant.
Right. Can you hear me now? Yeah, okay, perfect. So the numbers you can see at the bottom are the means, and you're really, the dashed line here is really referring to the median of the box plot. In both senses, whether you're looking at the mean or whether you're looking at the median of the whole thing, we find that we are still outperforming the open loop in here. And this is averaged over all the gauges in both domains. Now, whether 2%, whether you get an improvement of 2% after 18 hours, or perhaps maybe 20% after 3 hours, that's a question. I would definitely be interested in looking at more the 3-hour one person, because it has a lot more skill compared to the 18-hour one. But I mean, it's a point that we tried to make that across all the gauges, even after 18 hours, we're still a little bit better. So that's something. Yeah. Does that answer?
I think so.
Okay.
Another question in the room. Let's.
Yeah, thanks. Really interesting to see streamflow hydrographs in a talk here and all the data assimilation work. On the slide where you're talking about CONUS-wide prediction,
Yeah.
was that showing predictions or estimation, like forecast or?
The 1 hour forecast, so
1 hour.
the priors essentially.
Okay.
1 hour forecast, yeah.
And then the comparison with river forecast centers, is that with river forecast center 1 hour predictions
Yeah,
or?
the same 1 hour prediction, yeah.
Okay.
Yeah. And this is incomplete, this is very, very new, preliminary, we didn't have a chance to look at everything, but yeah. Dan, you have a
Okay,
question?
Dan.
Thanks for a really nice talk, Moha.
Sure.
I think the ATS feels intuitive because you have a sense that the information flows like water and you define length scales that way.
Yeah.
I was wondering if its utility could depend with the length scales of the forcing as well, though, right? Because
Yes.
you could be reaching over to another basin, especially for a large-scale storm. So where do you see trade-offs there?
Yeah, I think, Dan, you're hitting the nail on the head here. We really believe that, let me just go to the slide. That precipitation plays, the length scale with in precipitation should be somehow incorporated in this scheme. Right now, we're only looking at especially at the stream network, but adding in information from the length scale of precipitation is going to be very interesting, yet it's not easy. Very good question. Yeah. Not sure if we're going to do that very soon, but we definitely thought about it.
Anything online, Lisa?
There are 4 questions online.
Okay, maybe we should switch to online for a minute or two.
Thanks for a cool presentation. Do you have a sense of how this improves forecasts for larger versus smaller basins, or for basins in different climatological regimes? Yeah, good question. Yeah, I guess looking at what we consider today here. So we looked at West Virginia at the AN domain. Again, I'm not a hydrologist, but these are different, size basins, and we saw consistent performance across the different domains. And now we're looking at the whole CONUS domain. We feel confident with what we've seen so far that this has been robust across different size basins. I hope that answers your question, Ethan. From Michael, could you explain a bit further what is controlling when the inflation parameters are utilized? Excellent question, Michael. So there are different, parameters that go into the update of inflation. There is the bias, or how far your observation is from your prior ensemble mean. What is the current prior ensemble spread? What is the variance essentially in your ensemble? And the observation error variance. How much do we trust the observation? So all of these 3 things together are combined within this Bayesian scheme to determine how much the inflation can be updated. And from Tom, would there be benefits to including post-processing algorithms with your DA schemes, correction of historically observed errors biases? Do you feel the hybrid scheme should be able to capture many of these potential benefits of post-processing? Yeah, I think the answer is there in your question. Right now, this is my belief. The climatology with its, all of these past events that we see, I think it's contributing to a lot of the benefits in the prediction skill that we see in these seismographs. From DJ, great presentation for a hybrid method. Is there any potential benefit in calculating climatological background covariances based on subset of similar events rather than full climatology? Might be good use. Yes. So there are many different things. In fact, this is one of the points I mentioned on the slide for CONUS. We're gonna really dig deeper there. We are gonna tune the climatology in many different ways. Whether we're gonna look at similar events, perhaps do some, EOF analysis, and might as well, perhaps look at the machine learning for identifying similar events. So yeah, great point. We're gonna look into that, and perhaps we can collaborate on that together.
Okay, one more in the room at least.
Yeah, just thinking about operational potential. I don't have a good feeling for the sort of time cost or latency that would be incurred in running sort of the more complex of your systems. You do show that you can trim it down to a small number of ensembles, But if you can imagine, like during a big flood event, you might end up wanting like 2 hourly updates in which you rerun the whole system, update it, put out a new forecast. Is that doable over large domains, or
So,
given the computational resources
yeah.
you have?
I guess I can speak from, from the switch that we made, from these smaller domains to the entire CONUS domain. We had to really be smart about many different things. It definitely, the computational cost increased in a way that I wasn't expecting. But having the hybrid scheme, I guess, is going to be a lifesaver for us, just because we are massively cutting on the computational resources that we usually do with the ENCAF. Now, the other, I guess, a challenge would be when we, couple the whole thing together. When we couple with the LSM, initializing the whole thing every hour is going to be computationally expensive. We're still looking into that, but we are excited, and I don't see any showstoppers at the moment.
Any last question in the room? Okay, anything else online, or are we done?
We are done.
Okay, thanks to
Oh,
our.
excuse me.
Oh,
There is one.
Yes,
okay, and we'll make this the last question.
I'm happy to read it as well. There you go.
And can you clarify what you mean by strongly coupled in this context? Assimilating discharge will directly update soil moisture, assimilating soil moisture. Yes, that's exactly what I mean. And in fact, not only soil moisture, perhaps the snow observations as well. Essentially, whatever is happening in NOMP is feeding into WRF-Hydro and back and forth. Yep.
Okay. Thanks to Lisa and our audiovisual specialist, and thanks again, Moha, for a great talk.